Hydrides. Hydrogen combines with large number of elements including metals and non-metals except noble gases to form binary compounds called hydrides, and it can be represented as EHX. E is the element and H is the hydrogen, X represents the number. Okay. So, for example, BeH2. Also, it can be represented as EMHN. M and N are numbers, E is the element and H is the hydrogen. Example, B2H6. Okay. These hydrides are divided into three categories. First one, ionic or saline or salt-like hydrides. Second one, covalent or molecular hydrides. And third one, metallic or non-stoichiometric hydrides. Metallic or non-stoichiometric. Let us discuss one by one. First one, ionic hydrides. These are stoichiometric compounds. Stoichiometric compounds. Okay. These are formed when hydrogen combined with S block elements. Okay. S block elements form ionic hydrides. Okay. Now, these while during the formation, there is a transfer of electrons from metals to hydrogen atoms and hydrogen H minus ion is obtained. Example, in the case of NaH, Na plus and H minus ions are formed. In the case of Ca, Ca2 plus and 2H minus ions are obtained. Okay. Now, next properties. They are white crystalline solids and have ionic lattices, okay, and they behave like salts, so they are called as salt-like hydrides, okay. So they are white crystalline solids, have ionic lattices and behave like salts. Then they have very high melting and boiling points. Melting and boiling points. Okay, they are non-volatile and non-conducting in solid state. Okay, in solid state, they are non-volatile and non-conducting, but they are conducting in molten state or when they melt or in fused state. Fused state, they conduct electricity. Okay. So, during electrolysis, what happens? The positive ion moves towards the cathode and hydrogen ion moves towards the anode, and hydrogen gas is liberated at the anode. Okay. During electrolysis, example, NaH. NaH is dissociated into Na plus and H minus. Okay. This Na plus at cathode, what happens? Accepts an electron and forms sodium metal, and at anode, hydrogen liberates electron and form H2 gas. So, H2 gas is liberated at the anode. This reaction shows that this NaH, this hydrides contains H minus ions. Okay. Now, fourth property, These hydrides reacts violently with water and produces dihydrogen. For example, NaH, sodium hydride, reacts with water and form NaOH plus H2 gas. Okay. Next, fifth one. It burns, these hydrides burn spontaneously in air on heating, because during the decomposition hydrogen is obtained which is highly inflammable. For example, CaH2 dissociates into Ca and H2. This hydrogen gas obtained is highly inflammable. So on heating it burns spontaneously. Okay. Now sixth property, lithium hydride forms many useful reagents, many useful hydrides are obtained from lithium hydride. Okay. These are obtained because these hydrides are unreactive at moderate temperature with chlorine and oxygen. Okay. So these reagents are obtained. For example, 8LiH on reaction with Al2H6 aluminum hydride. What happens? A useful chemical LiAlH4. Okay, this reaction is LiAlH4 is a very useful hydride. Okay, it is used for hydrogenation. Okay, next another example, LiH on reaction with BH2H6 and forms LiBH4, another hydride which is also very useful. Okay, these are the properties of hydrides. Second one, covalent or molecular hydrides. Covalent or molecular hydrides. These hydrides are formed on hydrogen reaction with p block elements. Okay, hydrogen reacting with p block elements. These types of hydrides are obtained. Okay, example, CH4, H2O, NH3, etc. Okay, and these are volatile compounds. These are volatile. According to the relative number of electrons and the bond in the Levy structure, they are classified into three. First one, electron deficient molecular hydrides. Second one, electron precise molecular hydrides, and third one, electron rich molecular hydrides. Let us discuss one by one. First one, electron deficient molecular hydrides. Electron deficient molecular hydrides. Okay, these hydrides have lesser number of electrons than they required for writing the conventional Levy structure. Okay, they have lesser number of electrons. Lesser number of electrons than required for writing conventional Levy structure. Okay, these are formed from group 13 elements. Formed from group 13 elements. For example, in the case of BH3, this is electron deficient. Okay, so they polymerizes and form B2H6. Okay, since these are electron deficient, they can accept electrons. Okay, so they act as Levy's acids. Okay, now next, second one, electron precise molecular hydrides. Second one, electron precise molecular hydrides. In these types of molecular hydrides, they contain required number of electrons to write the conventional Levy structure, and group 14 elements are obtained. these elements are formed, these types of these electron precise molecular hydrides. Example, the tetrahedral geometry of CH4. Okay. Now, third one, electron rich molecular hydrides. In these types of molecular hydrides, they contain more electrons than required for writing the conventional Levy structure. Okay, and these have excess electrons to form and which contain one or more lone pair of electrons. So they contain excess electrons. Okay, one or more lone pairs of electrons are present in these types of molecular hydrides, or they are electron rich. Okay, these lone pair of electrons are seen around the more electronegative central atom. Okay, more electronegative central atom. So the more electronegative central atom is surrounded by one or more lone pair of electrons. Okay, so they are electron rich. This lone pair results in the association of molecules due to hydrogen bonding. Examples, these compounds are obtained by group 15 and 17 elements. Group 15 and 17 elements form these types of hydrides. Example, NH3. NH3 contains one lone pair, then H2O contains two lone pair, and HF contains three lone pair. Okay. If we draw the H2O molecule, the central oxygen atom, which is highly electronegative, and it contains two lone pair of electrons. Okay. Due to this lone pair, this angle is distorted, and this is the bond angle. Okay. These are some of the examples for covalent or molecular hydrides. Okay. Third type, metallic or non-stoichiometric hydrides. Non-stoichiometric. Okay. This contains group 3, 4, 5, that is D block. Group 3, 4, 5, D block, and F block elements. F block elements form these types of hydrides, metallic or non-stoichiometric hydrides. Okay. From sixth group, only chromium forms hydride, that is CrH. Then 7, 8, 9 group do not form these hydrides. Okay. These are called as metallic because they conduct electricity. Okay, so they are called as metallic hydrides. They conduct electricity. Then they are non-stoichiometric because they have variable combination being deficient in hydrogen. For example, take LaH 2.87. Okay, see, these are non-stoichiometric. Then YbH 2.55, another example. All these are stoichiometric. These have deficient hydrogen. Okay, deficient in hydrogen. Then TiH 1.5 to 1.8. These are examples. Okay, so they are non-stoichiometric hydrides. So in this case, the law of constant composition does not hold good in this case. We already discussed while studying the law of constant composition. Okay. Next, we can see some of the properties of metallic hydrides. They have the properties similar to parent element. Similar to parent element. Okay, their properties are similar to parent element, that is parent metals. They are hard, they have metallic luster because they are metallic in nature. So they are hard, metallic luster, conduct electricity, Okay, these are the properties of these hydrides, and they have magnetic properties also. They are less dense than parent metal. Okay, they are less dense than parent metal. Okay, now these are called as interstitial, metallic or non-stoichiometric or interstitial hydrides. Because earlier it is found that hydrogen atoms are present in the interstices of the metal lattice, but later it was disapproved. Okay, so these are disproved. So due to this, they are called as interstitial hydrides. Okay, transition metals have the property of absorption of hydrogen. Example, platinum and palladium. These are used during the hydrogenation and catalytic reduction. Okay, these are used for the hydrogenation and catalytic reduction because they have the property to absorb hydrogen, which is used in the catalytic reduction and hydrogenation reactions. Example, platinum and palladium, which can absorb large amount of hydrogen. So they are used as storage media. Okay, they are used as storage media, or they are used in cars for fuel cells. In fuel cells these are used. Okay, these are examples for metallic or non-stoichiometric or interstitial hydrides. Okay.